Good morning, everyone. This is lesson 37 of geometry, and we're talking about dilatations. Dilatations is the action of dilating things. So, if you've ever gone to the eye doctor, you've had to possibly have your pupils dilated. Um, what happens when our pupils dilate is they become wider, and the purpose for that is when it's dark outside or we're in a dark environment, essentially our pupils widen so they can capture as much light as possible so we can see more clearly. So if you've ever gone from a very light room into a dark room, it's very, very hard to see at first. And then over time, your eyes become accustomed to the darkness and you can start seeing better. That's because our pupils are actually going from a very a much smaller sort of radius. So that's when they're a lot smaller. And then when they go into that dark environment, all of a sudden they start slowly widening over time, and they're trying to capture more and more light. Now, how does this apply to math? Dilatations is about stretching objects and shrinking objects. It's a fancy way of stretching, and it's a fancy way of saying stretching and shrinking objects. So we're going to talk about some of these examples right now. Um, we'll start off simple with just lines, and then we'll become more advanced as we talk about larger shapes and stuff. So my first example here is I have a series of lines, and my O is my origin point. That's important for us to remember what origin point is. Remember, it's always 0, 0 on every single graph. Um, so here's my origin point, and all the work that you're doing with dilations is always going to be having an origin point. If you don't have an origin point, it's going to make it really hard in order to understand how you stretch it or how it stretches effectively. Because when you stretch or when you shrink an object, the shape of the object should not change at all. Okay, so if I'm stretching or if I'm shrinking a square, at any point that I'm stretching or shrinking it, it's always a square. It's never going to turn into a rectangle. Okay, and the way it would turn into a rectangle is if I only applied the rules of dilation to only one part of the shape. But I don't do that. I apply it to all parts of the shape. So here's my example. I have line A, or I have point A and point B, and then I have O as my origin. I have prime B and prime A. So what I'm going to say is I can even just count this out. I measured this line, origin to A, or OA. Line OA is equal to 1, right? And line OB is also equal to 1. Now, line O to A prime, that's that little sign right there, that's actually prime. Line O to A prime is 3, and line O to B prime is also 3. If I wanted to, I could now describe the relationship between line OA and OA prime as 3 to 1 if I write it out correctly. So OA prime to OA is 3 to 1, which is the exact same as the other one, which is OB prime to OB is 3 to 1. So that means what I'm doing actually is I'm stretching this line. It's becoming 3 times larger than it was originally. Okay, so before it was 1, now it's 3. That means I'm stretching it 3 times. So that is a dilation of 3 to 1. Okay, so it's getting bigger. Now, it's really important for us to understand and pay attention to the order of the ratios. If I were to go the opposite way and say O prime to OA, that's 3 to 1, or OA to OA prime is 1 to 3. Now, I want to understand the difference between that because I should probably always compare my new to my old, right? And the reason I know this is new and this is the old one is because it's A prime. That means it's written after, right? Because prime means image. It's an image of it. So you can't have an image of something unless you have an original something. Okay, so I want to make sure that I'm doing this in the correct order. I want to have my primes always as my first number and my originals as my second number. All right, so here I have an example for us to work on. And notice how I have a point of origin. It's outside the circle. Now, it's important for me to have this outside the circle because it makes it easier for me to count. I could realistically have my point of origin right here if I wanted to. That would have probably also worked, but I chose to have it here. And now what I'm saying is my rule is my prime to my original number is 2 to 1. That means everything needs to be stretched out by double. Now, I'm always going to start my point of origin. So what I'm going to do is I'm going to say, okay, point of origin to A, that is 2. So my A prime is going to be right here. A prime is there because this one's originally 2. That means my next one should be double that, so I should be at 4. So it's 4 boxes away. 1, 2, 3, 4. And there's my A prime. Now this one I can go down C and say, okay, well, this one goes down to here. And this is where my C prime is, right? And then I have this one. Now this one's a little bit odder because you can't actually count it perfectly, but I'm going to just count the width of the boxes across. So diagonals, 1 diagonal, 2 diagonal, 3 diagonal. That means I need to go 6 diagonals down. 3 more. 1, 2, 3. And this is my new B prime. So now I have a new shape with my primes. And I can go across here and draw this line, and draw this line, and draw that line. And I have a new shape. And this is my new shape, which is A prime, B prime, C prime in ratio to A, B, C, make it a triangle, is equal to 3 to 1. Oh, sorry, no, not 3 to 1. 2 to 1. My bad. Right? My original rule was it's 2 to 1, and then my triangle, actually, if I were to look at this, is going to be 2 to 1 as well. Right? Now, I have another example right here, which is with a rectangle. So my rectangle, I'm going to have a scale factor of 2. So what is a scale factor of 2? It's actually the exact same as this ratio right here. It's just, I'm just describing it in a different way. A scale factor of 2 is saying 2 to 1 or 2 over 1, right? These are all three the exact same values. And remember, I always have my image first. So my image is in ratio to my original. Okay, so that means my image should be 2 times as big. So if I ever have, so this is called scale factor actually, whenever I have a scale factor of greater than 1 or 1 or greater, that means my object is going to become bigger, where less than 1 is going to become smaller. So this is my original, and I'm going to make this doubled in size because my scale factor is 2. So that means I have 1, I want to put another dot here, and I want to put another dot 1, 2, 3, 1, 2, 3 here, and that means these are going to connect here. And my new rectangle is going to look like this. So this second rectangle, I'll say this is A prime, and this is A. My new rectangle is twice as big as my old one. Now, if I were to ask the question, I hope you know the answer to this. Are these two rectangles congruent to each other? Well, no, they're not, right? Because they don't have the same, they aren't the same size, but they do have similarity because they have the same ratios. This was 3 and 1. This is 6 and 2. That means that they have the same ratios in between sides, and they actually have the same dimensions. Therefore, they are similar, but they're not congruent. Right? So this is on page 177 through 179. I think the best questions to do are 1, 4, 6, 7, 8, 10, 11, every other one. You could do different ones than that, but these are the ones that I thought would be the most valuable for you to complete. I hope this is helpful. Please send me a message if you need some help. We also have a math block in about an hour's time.